Hello chemists, this next video lesson is going to cover rate laws. A rate law is a mathematical relationship or equation used to calculate the rate of a reaction. In our last video lesson you were introduced to the rate of a reaction, and a rate of a reaction can be described by how quickly the products get produced or how quickly the reactants get used up. But we gave you the rate in each one of those cases, and you were able to use the stoichiometric relationship to calculate how much of the product gets produced, or not how much, but at what rate the product gets produced if we knew the rate of the reactant, and vice versa. But this is an actual equation that is used to calculate the rate of a reaction. Here's my general form of a chemical reaction again, where A moles of A plus B moles of B give you C moles of C and D moles of D. This is the general form of a chemical reaction. And a general form of a rate law looks like this, where the rate is equal to K times the concentration of A promoted to the X power times the concentration of B promoted to the Y power. I'm going to talk about each part of this rate law here line by line. First, only the concentration of the reactants are included in the rate law. As you can see, the concentration of A and B, as from this general form of the reaction A and B, were used to determine this rate law. K is called the rate constant, and the rate constant is unique to a reaction at a specific temperature. So no two reactions have the same K constant. Now notice there are exponents involved in the rate law, X and Y, and also notice that X and Y are not actually reflected in the chemical reaction itself, because X and Y don't actually stand for stoichiometric coefficients. X and Y in this case are called reaction orders. And these reaction orders will be described on the next slide, but they are exponents that are used to multiply or promote each reactant to a particular power. Mathematically, they're used as exponents. But you can't just simply look at a chemical reaction and determine what the reaction order for each reactant is. In fact, the only way to do this is to use experimental data. So I'm going to scroll up a little bit to give myself some more room. And that's an important note to point out about reaction orders. You cannot look at the stoichiometric coefficients and determine a reaction order. It can only be determined using experimental data. Now, you might be asking yourself, what does that experimental data really look like? We will explore that in a few slides. Before we look at experimental data, let's talk a little bit more about what reaction orders are. This is best illustrated using a little table. The three most common reaction orders you will see are zero order, so you'll see A to the 0 power, or you'll see first order, which is A to the first power, or second order, which is A to the second power. Now, if a particular reactant is zero order, you would observe it through experimental observation, and here's what you would see. You would, in fact, look at data for 2 experiments, and in each experiment, you look at doubling the concentration. So in one experiment, it's maybe 1 molar, and in the next experiment, it's 2 molar. But if you observe that the reactant has doubled in concentration, but the rate remains the same, then you can safely assume that the reaction order is zero order. Now, a next situation that might occur is you see that 2 particular reactions and you compare the rates, and if you double one of the reactants and the rate happens to double, or if you triple the reactants and the rate happens to triple, everything kind of goes along proportionally. If that's the case, the reaction order with respect to that reactant is first order. In the last situation that you most commonly see is if you take a look at 2 different experiments and you notice A changes and you double A and then the rate goes up by 4. Or if you triple A and the rate goes up by 9, then you can safely assume that the reactant or reaction order with respect to A is second order. So in summary, if the concentration doubles between 2 experiments and no change in rate was observed, then that particular reactant is zero order. If the reaction doubles in concentration from one experiment to another and the rate also doubles, then you can expect it to be a first order with respect to A. And if the concentration doubles between 2 experiments and the rate goes up by a factor of 4 or quadruples, then you expect the order of that reactant to be second order. So here's a set of experimental data that you can expect to see something similar to this. I first want to draw your attention to the chemical reaction itself. We've got some NO and some H2 reacting to combine and make N2 and H2O. The reaction was carried out in 3 different experiments, as you can see up here, and in each time you have the chemical's concentration listed and the rate. So with this information, you can determine what the rate law is of this particular experiment at this particular temperature. So the first thing I'm going to do is compare experiment 1 and experiment 2. I notice that in experiment 1 and 2, the concentration of NO remains constant, but the concentration of H2 doubles. Now, if I see the concentration of H2 double and the rate doubles, then I can safely assume that this reaction is first order with respect to H2. So I begin generating the rate law. It all starts with rate is equal to K. And then I start filling in my reactants. I got H2 and I put that to the first power. I can just simply say H2 without an exponent that means to the first power. Notice that experimentally, the order is observed to be first order, even though the stoichiometric coefficient for H2 is 2. So notice they're not the same. We do not worry about the stoichiometric coefficients when determining reaction orders for reactants. So the next 2 experiments I'm going to look at is experiment 1 with experiment 3. And notice this time I have experiment 1 and 3, I hold H2 constant and I double my NO. Now when I hold H2 constant and double my NO, my rate goes up by a factor of 4, which means if I double this and this goes up by a factor of 4, I can safely assume that NO is second order. So I've just generated my rate law for this particular reaction using experimental data. So the next thing I can do is calculate K. And what I do is pick one experiment. And I plug in the concentrations for NO and H2 and the rate into my rate law and simply use algebra to solve for K. I'm going to use experiment 1. So here I plug in the numbers and I have everything except K. When I ask what is K, what I'm really mean is calculate K. And it's worth noting that the units are very important for K because they change depending on the reaction. And so often on the AP test, they'll ask you to calculate K, and you want to make sure you include the proper units. So I'm going to copy this down here so I have a little bit more room to work, and I'm just going to scroll up because I don't need that experimental data anymore. I just need the rate law. I'm going to keep everything on the left-hand side the same. Nothing changes there. It's 1.23 times 10 to the negative third molarity per second. But over here, I'm going to combine like terms and multiply my numbers together and get a value. Now, 0.1 to the first power times 0.1 to the second power equals 0.001. And the new units are molarity times molarity squared, or molarity cubed. Now using simple algebra, I'm going to divide by 0.001 molarity cubed on each side, and I'm going to cancel out everything on the right, so I isolate K by itself. So I do the math. I take 1.23 times 10 to the negative third, and I divide by 0.001, and I get an answer of 1.23. But the question comes up is, what do I do with these units? Well, I have molarity per second per molarity cubed. Now, if you look real closely, molarity on top will cancel out one of the molarities in the denominator, but it still leaves me with a molarity squared in the denominator. Now, if I'm smart at math and algebra and I rearrange these variables, basically when you have something in the denominator, it's the same as multiplying by its inverse. So I'm going to take it out of the denominator, I'm going to multiply by its reciprocal, which is 1 over molarity squared, to kind of get that out of the denominator. And now I'm going to combine these to figure out what my units are. So the answer is 1.23 1 over seconds times molarity squared. Now that looks like an awkward unit, but it is indeed the correct unit. Now instead of using fractions to represent our units, we're going to use negative exponents instead. Because as you know, if you have like 1 over seconds, that's the same as saying seconds to the negative 1 power. And so if I rewrite my units using negative exponents instead of a fraction, what I have is seconds to the negative 1 power, molarity to the negative 2 power. So in this chapter especially, you will see the units for K expressed as a negative exponent. So my final answer, my final answer for K is 1.23 seconds to the negative 1, molarity to the negative 2. That's my K constant. So all of this work that I did just here was solving for k. I need to go ahead and do the last part of the problem, which is actually answer a hypothetical situation. Now that I have my k constant and I have some concentrations listed here, what would be the rate using that k constant in these concentrations for NO and H2? So I just simply plug it in and solve for the rate. So I set up my work. I got the k constant that I just calculated, and I got my two concentrations, making sure that I square this one. Now when I'm taking a look at my units, I've got molarity squared times molarity, which is molarity cubed, molarity squared times molarity, which is molarity cubed, times molarity to the negative 2 power. So in fact, what those do is they cancel each other out. I'll use green to cancel out my units, leaving me with just one molarity. And I also have seconds to the negative 1 power. My units for rate are always molarity per second, and that's good. So what the k constant provides for us is actually a bunch of units that are going to cancel out, and as long as the rate is equal to molarity per second, I know I've got the k constant units correct. So the last thing I need to do is just simply calculate my numbers. 1.23 times 0.05 times 0.150, and the correct answer is 4.61 times 10 to the negative fourth. And my units, once again, are molarity per second. So there's some units that you need to keep track of here. A lot of students get mixed up with the units. It just takes practice, keeping your fundamental algebra in the forefront of your mind. Stuff needs to cancel out. The k constant units need to be exact, or else you're going to get some incorrect answers. But I truly believe that it'll come along with more practice. Well, that brings us to the end of this little video lesson on rate laws. Thanks for listening.